Now let us prove Merten's theorem. The proof will be a combination of lots of tricks in analytic number theory. You will see lots of acrobats. Henceforth, we assume that in the proof, all the integers are positive, so that I'm not going to emphasize that m and n are strictly greater than 0. I will omit this greater than 0 part. S of x is equal to the summation over mn less than or equal to x GCD of m and n is equal to 1 of 1s. The first thing we will do is that we are going to apply a very simple theorem in analytic number theory to break this sum into two sums. Of mu of d. If you don't remember this fact, let me remind you. You can find this in the theorem 2.1, page 25 of Apostol's Introduction to Analytic Number Theory. Theorem 2.1 says the summation of mu of d's, where d divides an integer n, will be equal to 1 if n is equal to 1, and 0 if n is greater than 1, where this mu function is a Mobius function. If this is the prime number decomposition of an integer, then the Mobius function on this number will be defined as -1 raised to the power k if a1 all the way through ak are all equal to 1. Or in other words, this number, this integer, is just a product of k different prime numbers. In this case, we usually call this the square-free integer. And this guy is defined to be 0 otherwise. Namely, if there is a square in this integer. And this equality follows immediately from this theorem. If GCD is equal to 1, this part will give you 1. If GCD is greater than 1, then by the theorem, this sum will become 0. So you will see that this single sum is really equal to this double sum of mu of d's. Okay, now what can we do with this double sum, this iterated sum? The natural step for us will be to try to switch those two sums, to sum it in another way. This is the classical Fubini idea in mathematics in general. Whenever you see a double sum, you should always have an urge to switch that sum. Hopefully, you'll get something new. So let's do it. I claim that this sum will be equal to this one. If you consider sum over m and n first, and then take the sum with respect to d. Do you see immediately why this is true? This is true because we have the following bijection. For any x greater than 0, there is a bijection f from the set where elements are represented, from the set where elements from the set where the elements are represented with respect to the first sum to the set whose elements are represented with respect to the second sum. The elements in the first set are represented by m and d corresponding to the variables in this double sum m and d. And the elements in the second set is represented by rsd corresponding to the variables rsd in the second double sum. And this bijection is given by sending m, n, and d to m divided by d, n divided by d, and d. And conversely, there's an inverse to this map F given by sending the triple RSD to RD, SD, D. So this is the inverse to F. It shouldn't be hard to foresee that this F is really a bijection by composing these two maps in two ways. The validity of this sum switching precisely follows from this bijection, or I should rather say one-one correspondence. This bijection is a change of variable formula. Now let us continue. The last equation can be rewritten as, because mu of d as a function of d does not change when you take this sum. This sum has variables r and s, which is independent of d here. So mu of d is really a constant when you do the first sum. So you can pull it outside. And this is equal to, now you can break this sum into the product of two sums. Each of them will be precisely the floor of x over d. So you get x over d squared. So we have transformed this s of x, defined to be this sum, into this. In particular, our main achievement is to move this x into the summand so that this x really plays some role as a variable of a function. Moreover, we are able to remove this GCD condition by introducing the Mobius function mu of d, so that we could use some good estimates from analytic number theory to give a bound for this. So now let us see how to give an estimate to this. This guy can be first rewritten as the summation of mu of d times x over d minus the decimal part of x over d squared. Because the floor of a number plus the decimal part of it is equal to the number itself. And now this guy, if you break down this square, this gives you the summation of mu of d times x over d squared minus twice of the decimal part of x over d times x over d plus the decimal part of x over d squared, which is equal to. Now we are going to do nothing but simply to separate this sum into 3 sums. I really did nothing in here, but separating them. So let me call this part 1, and this part 2, and this part 3. And now let us look at part 1, 2, and 3 separately. The easiest part for us to bound is the part 3. So the absolute value of part 3 will be majorized to simply the summation of those d less than or equal to x of 1s, because the absolute mu of d is less than or equal to 1, and this decimal part is always bounded by 1. So you get this trivial bound. And this is less than or equal to x. So part 3 is really a big omega of x by definition. The second easiest part is the part 2. The absolute value of part 2 will be less than or equal to, again, we'll give this a very generous bound by majorizing the decimal part of x over d to 1 and this mu of d to 1. So you will get this is less than or equal to 2x times the summation of 1 over d with d less than or equal to x. So we put this x to the front. So how to bound this guy? If you remember calculus very well, this will be something close to the logarithm of x. Specifically, this will be equal to 2x times the logarithm of x plus some constant plus the big omega of 1 over x. If you don't remember this result, let me remind you that you can find this in the theorem 3.2, page 55. This is the theorem 3.2 part A of Apostol's Introduction to Analytic Number Theory. And when x is large, this whole thing will be a big omega of logarithm of x. And if you put this x inside, this guy is a big omega of x times logarithm of x. So part 2 is a big omega of x times log x. And in the end, we get 2 plus 3 is a big omega of x times logarithm of x, because this guy grows faster than simply x. So all it remains to bound the first guy. Okay, now part 1. The first thing we will do with the part 1 is that we want to pull out this x squared from this sum. This is the finite sum. We rewrite this as a difference of two infinite sums. One is from d equal to 1 to infinity of mu of d divided by d squared, and another is summation over d greater than x of mu of d divided by d squared. Both of these two parts are absolutely convergent because mu of d has the absolute value bounded by 1. And the sum of 1 over d squares is convergent. So it makes sense to write this finite sum into the difference of those two sums. And this, if you look at this part is equal to 1 over zeta of 2. Let me copy the second part down and I will explain this to you. So here we are using the theorem 11.7, page 231 of Apostol's Introduction to Analytic Number Theory. In case you get confused, I should remind you that the summation of 1 over n squared when n is from 1 to infinity is zeta of 2 by definition of zeta, the Riemann zeta function. And the summation of mu of n divided by n squared, where n is from 1 to infinity, is equal to 1 over zeta of 2. This is by theorem above, namely this theorem, where the Euler's identity is involved to prove this, as well as the multiplicativity of the Mobius function. And now let us take care of this part. This part, taking the absolute value, is bounded by, if we just majorize the absolute value of mu of d, this is less than or equal to the summation over d greater than x of 1 over d squared, which is big omega of 1 over x. This is by the theorem 3.2c of Apostol's book, page 55. So this guy divided by 1 over x will be bounded by big omega of 1 over x divided by 1 over x, which is bounded by a constant. So this tells you that this infinite sum involved is nothing but a big omega of 1 over x. Therefore, this last equation will be equal to x squared divided by zeta of 2 plus x squared times the big omega of 1 over x. So in the end, you will get 6 over pi squared, which is the reciprocal of zeta of 2 times x squared plus the big omega of x. Now combining the estimates for 1, 2, and 3, because 2 and 3 combined is a big omega of x times logarithm of x, which grows much faster than simply x. So in the end, we will get s of x is equal to 6 over pi squared times x squared plus big omega of logarithm of x. We take the one that grows faster. And we are done with the proof of Merten's theorem.